Looks good.
Perfect. Okay, lovely. So yeah, I'm Emer Jones. I'm a BBSRC funded PhD student at the CBU here, supervised by Tim Keatsman and Matt Lamban-Rolfe. And today I'll give a very introductory primer to deep neural networks and their use as models of the ventral stream. So if I show a toddler or a young child any of these images, they would quite happily be able to tell you that it's a dog, even though the visual features in all of these images are very different. So it's actually quite a complex task that the ventral stream is doing. Now, even if we look at low resolution grayscale images of these handwritten digits, it would be very non-trivial to try and formulate an algorithm that would take the pixels of any of these images of a 3 and output what digit the picture is representing. And this is the type of task that deep neural networks excel at. And I'd like to show you what they are and how they do such a task. So first of all, the core unit of a deep neural network is a node, which is essentially a very abstracted neuron. And a node can be thought of as a junction, where it takes in input signals that are weighted by connection strengths. And that weighted sum is passed through an activation function. And the output signal is also weighted by a connection strength called the bias. And activation functions, many activation functions are used. Two of the very common ones are ReLU, a rectified linear unit, is just a threshold. So it will output any value that's positive. Sigmoid is another activation function that's frequently used. And this compresses the values to range between 0 and 1, effectively making them a probability. So in most basic artificial neural networks, nodes are arranged in layers, where every node is, each node in a given layer is connected to every node in the next layer, as we can see. Now, in the case of an image classification network, the input layer will be the nodes in the input layer will be the pixels of the input image. So of course you'll need a lot more than 3 to represent your image. And these activations will pass through the network, and the output layer here, if you pass the output activations through that softmax function, the output layer nodes will represent the probability that the input image belongs to each category. So we can see here that the node with the highest value is the model's prediction of dog. So crucially, a deep neural network then is just an artificial neural network with more than one hidden layer. And deep learning, in deep learning, parameter values are not hand engineered. So the strength of each connection that we see here is learned during training. Rather than being hand engineered. So you can have many, many of these parameters. You don't have to individually tweak them, which is where the strength of deep learning comes in. So next I'll show you an animation of a trained deep neural network in action. So it takes a 28 by 28 pixel input image. The resultant activations pass through the neural net, and the resulting highest valued readout node displays the model's prediction. Here it's getting it correct. It's classifying the image as a 7. So let's think about how the parameters then are learned. So in this training run, we have an image of a 3 and its corresponding label. And the difference, so we'll pass this image through the network. The activations will filter through to the readout layer. And the difference between the readout prediction that's seen here and the target is the cost. So this is the error in this training run. So this cost is propagated back through the network, and the parameters, so all the weights and biases, the connection strengths, they will all be adjusted a small amount per training run according to how they contributed to this cost or error. So now I'm going to show you actually how this sort of model can be built and trained. So many people might assume that in order to build this kind of model, the code would be quite complex, but using a Python-based library called TensorFlow, and there are some other libraries as well out there, it's surprisingly easy using these frameworks to build and train a simple neural net model. So I'll show you the code as well as explaining what's going on. So after some imports, first of all, we're just going to load in the data set. And here, the data set of handwritten images is called MNIST, and very usefully, it's an internal data set in TensorFlow. So the shape of these, we can see that we have 60,000 images, and they're 28 by 28 pixels each, and we've corresponding 60,000 labels. And then in that test set, we have 10,000 28 by 28 images as well with their 10,000 corresponding labels. This is the data we've just loaded. And first of all, what we'll do to replicate the model that you saw in the animation is we're going to flatten out those two-dimensional images to just a single dimension of 784 nodes. We'll normalize the values so that they are now float or decimal values between 0 and 1. And we'll define the model architecture. So here we'll define that we want a 784 nodes in the first layer. We want 2 hidden layers with 16 nodes each. And we want a readout layer of 10 nodes, 1 per category. And we'll pass that readout layer through a softmax such that the output values will be probabilities of the image being in each of those categories. So next we'll define functions we want the model to use. The loss will determine exactly how that error or cost should be calculated. And the optimizer will determine exactly how the parameters should be adjusted in each training run in response to the error or the cost. And we want to use accuracy as our metric. So we'll fit the model using the training set. We'll run it for 10 epochs, which is definitely on the low end, but perfectly fine in this kind of simpler case. And we'll evaluate on the test set. And we can see already that we're getting an accuracy of 93%. Something to note though is that, so just taking a look at the number of parameters here, we have about 13,000 parameters. Now, this is quite a small number of parameters in terms of deep learning models, but the power of deep learning can be seen here because trying to manually kind of hand engineer 13,000 coefficients would just be infeasible. So the next thing we might want to do to kind of upgrade this minimal working example is to use a nonlinearity in every layer. So at the moment, we just, other than the softmax at the end, the rest of the model is all linear. And actually, many linear layers are equivalent to just one larger linear layer. So to get the benefit from the depth of the model, we're going to add a nonlinearity called ReLU to each of our layers, to each of our hidden layers. And this is just going to be a threshold that outputs positive values. And we can see that the accuracy here jumps a bit more. Now, in practice, fully connected layers like the ones you've seen are inefficient and impractical for larger models. The number of parameters quickly gets pretty out of hand. And it's an inefficient way of going about this task. So what we're going to do is make use of convolutional layers. And these are the foundations of most computer vision deep neural networks. And this is based on the notion that a feature that's useful in one part of an image will probably be useful in another part too. So a convolutional layer consists of kernels, such as this one. It can be thought of that the kernels kind of swoop over the image and output, each kernel will output a feature map. And this will show where this feature is highly present and not so present in the image. So here we can see kind of the diagonal structure of these windows having higher values, but over here, there's not much diagonal structure. And so we're not seeing very much in the feature map. So ultimately, a convolution is just a weighted moving sum. And this sharing of weights leads to very much increased computational efficiency, hence their widespread use in computer vision models. So what we'll do is, rather than flattening out the images, we're going to leave the images as 28 by 28. And in fact, we're going to make it explicit that the image is 3D. So it's grayscale, so there's just one channel. In color images, you'd have 3 channels here. So you'd have red, green, and blue pixel input spaces. So we'll build our model. And so we'll replace the 2 dense, fully connected layers, hidden layers, with 2 convolutional layers. And so each layer will have 8 kernels that are going to move over the image and produce 8 feature maps. And these then will be downscaled using max pooling. So just in every grid of 4 values, only the highest one will be kept. And these will all be flattened out before again reaching our 10 readout nodes as before. And note the number of parameters here. So we have far fewer parameters, but the accuracy is higher. And so convolutional layers are pretty much the foundation of most, if not all, computer vision deep learning models. Finally, just like in the animation that you saw, we can do single image inference. So we can input a test image and get a predicted label. In this case, it's getting it correct as an 8. And so that was a very simple example. In reality, you'd probably want to use higher resolution, kind of more naturalistic color images. Your data set would probably have a lot more than 60,000 exemplars, and you probably want to classify into more than 10 classes. So typically classifying into hundreds of thousands of classes. However, ultimately the framework for doing this is the same, and this kind of very simple TensorFlow example I showed you can be expanded hugely into kind of quite sizable code pipelines with lots of flexibility, all just built around this basic framework. And these are the kinds of things that you would want to add into your model in order to expand its use and flexibility. For example, not using an internal data set and building much bigger models. So far, I've just spoken about deep neural networks and not how they might be used as models of the ventral stream. So already, these models can be seen as a functional model of the ventral stream in terms of them being end-to-end models from pixel space to an objective such as classification. Although they're loosely inspired by biological neural networks, they weren't designed as models of the brain. They were designed with an engineering goal in mind. However, they are in fact actually useful mechanistic models of the ventral stream, and they're the best models of the ventral stream at a high information processing level in terms of their ability to predict neuroimaging information. And we can see that there's we will see that there's a good degree of similarity between the representational structure of deep neural networks and the ventral stream. So there are similarities between early layers of the models and early visual cortex, and also between later layers of the model and inferior temporal cortex. So let's take a look at some ways in which we can see this similarity. So the first way we can see the similarity between deep neural networks and the ventral stream is in the features the model learns. So convolutional kernels here, they're learned, they're not coded, and they represent the features that the model has learned are useful. And as it happens, if we look at kernels in early layers, they resemble kind of Gabor filters and color blocks. So these are similar to the features for which early visual cortex neurons are selective. And then if we move to later layers and look at the kernels that are features that are learned there, the features are much more complex and abstract, kind of involving textures. We can kind of see honeycomb, birdish type stuff. And this is not dissimilar to neurons in later regions of the ventral stream being selective for more complex features. With regard to, so that was in terms of the features the model learns. With regard to the activations or the node values from each layer of a deep neural network, we can see that the representational structures throughout a deep neural network are actually similar to a ventral stream's representational structures. So here on top, we can see representational similarity matrices, which are a good way of visualizing and showing the representational structure of a model or of the ventral stream, in fact, from fMRI data. And on the top, we can kind of visually start seeing the similarity in the representational structures. Now, if we head here to the bottom left, this is showing the correlation between the representational structure of early layers and of late layers from a deep neural network, and the correlation between that and early visual cortex activations from fMRI. We can see here that it's early layers that are more similar to early visual cortex, while over here it's later layers that are more similar in terms of the representational structure to IT. So this is a very active field. There are lots of labs working to build and train models with increasingly greater mechanistic similarity to the brain. And just within the past 2 years, there have been some really great reviews about different work that's been done to build more models that are more mechanistically similar, including this one that just came out 2 weeks ago. So I hope that that kind of whirlwind introduction to deep neural networks and how they work and their use as models of the ventral stream was interesting and are useful. Apologies if it was too basic for those who are already familiar with deep neural networks. And also the code that I showed and these slides are available at the GitHub link. Thank you very much.